if Ken Magliosi's not here in this session, well, if you talk to Mr. Magliosi, he can help you, and I gave him directions 5 or 10 years ago on how to build a Van de Graaff. All you need is a roughly, it doesn't have to be a perfect sphere. You need a roughly spherical shaped upper terminal, good conductor. I made mine in 1951 out of a copper hanging flower pot. And the column, there's a number of places you can get a very nice column. If you've got a bird feeder, that's a round bird feeder that all the parts come apart. You can use that as your insulating column. The ground base can be any flat piece of metal and tie it in to the ground side of your electric supply. Okay, now let's talk a little bit about how this particular Van de Graaff works. We all know that if you get friction between two dissimilar materials, you can get an electric charge. This happens to use, let me take that off a little bit. This happens to use a belt made of rubber, and on the top, the upper pulley is a plastic. This one looks like lucite, which is what I happen to use on mine, which I built 60 years ago. Rubber on lucite gives you a good charge. I will tell you where you can go on the internet. On the internet, you can go nice here. Put that into Google. Once that into Google, and you will see it comes up with a series of how readily things give up electrons. And what this uses is rubber on lucite. The rubber gives up electrons very easily to the lucite. You can take any two materials that are on that triboelectric series, and as long as one of them is reasonably flexible, you can create an electric charge. What happens is we create a charge by, the rubber gives up electrons easily. So the friction is rolling friction. The electrons are deposited on the inside, on the lucite from the belt. What does that do? Immediately, electrons want to repel any other electrons that are near them. The ones on the lucite can't move. They don't move very well because it's not a good conductor. But they can repel the electrons that are in the new belt that's coming up, and they are collected. They are collected by the collector points that are up at the top, which is electrically connected by these copper wires to the sphere. Once they get on the sphere, they want to get as far away from those miserable other electrons as they possibly can. It's interesting. Like charges repel, unlike charges attract. And that's what takes place here. So what we get is we start removing electrons from the belt. And on the bottom, it doesn't come off easily, but on the bottom we have another pulley, which is a metal pulley, actually aluminum. The aluminum pulley is at ground potential, positive. When the electrons are removed, we'll call them minus, and they are removed with the collector points and connected to the sphere, it leaves the rubber belt is missing electrons. When I have a deficiency of electrons, it means I have a positive charge. A positive charge, then, if this is the direction the belt is running, a positive charge is carried down the belt. When it gets here, we have some spray points that are connected to what I would call the ground. It's a long distance, but the metal box there is connected to a ground wire in the cable, which is plugged into the wall outlet, which goes all the way to ground. Ground is a limitless sink of electrons. What that means is I can dump electrons into ground continuously without changing the potential of where I'm dumping it in. It's not exactly true, but it's close enough. So I can dump electrons into ground, or I can supply electrons from ground. So on the way up, I put the electrons back on. This is why I like chalkboards. Put the electrons back on the outside of this. They come up here, and remember, this is the plastic one that continues as a negative charge. And the negative charge sees these extra electrons here, chases them over to the collective points and to the sphere, and keeps the sphere maintained at a potential high above ground. So this is a negatively charged Van Graaf generator. You can make it a positively charged Van Graaf, but it takes a little bit more equipment and a little bit more work to do it. All right, well, let's move on that. If there's any questions that you have at any time of doing this, just speak up. What we want to do is investigate. Remember I mentioned something about an electric field a little while ago. What do we mean by an electric field? Well, let's turn it on and see if we can show on an electric field. Around that surface, there is an electric field. That means there's a force, an electromagnetic force is developed that radiates from the sphere. Since it's a sphere, theoretically, those electrons, the electric field caused by that excess of electrons on the sphere, that field extends at right angles to the sphere and outward, all over the sphere. There's an electric field. And if I get myself close enough, can you see that? It's getting hotter. So we're getting rid of some of the waste. Well, how can we demonstrate that we in fact do have an electric field which is radiating outward from the sphere? Well, it's pretty easy. I will attach a little bit of tissue paper. Now, if our theory about the electric field is correct, that piece of tissue paper, once I get a good charge on the sphere, should go straight out. Let's find out if our theory is correct. Oh, my goodness, look at that. Why does it have a little dip at the end? What are the forces acting on that strip of paper? Gravity is one. The electromagnetic field is pushing it away, and gravity is pulling it down. As the electric field got stronger, it took out the now, if I discharge it, it goes right back and recharge it. Now, that tells you we're getting hotter. Kevin, we're getting rid of the voice. By the way, the Van de Graaff is loaned to the school by Groton Electric Light Company, I guess is your full name. And Mr. Kelly is the gentleman who brought that over with his assistant, Pam. So we've shown that at that spot, at least, at that spot, the field extends exactly outward from the. Well, we're engineers. We want to really do a scientific study. Do we really know that field exists everywhere? Well, let's put a couple more strips on. Put one here.
Salt, pepper, add flavor.
Let's put one directly on the top. We've got three of them on there. All three should be staying away from each other because they will all have a negative charge. They're all going to theoretical. You only want to prove the theory. Is that where I put them? Well, is that enough? We're all good engineers here. Is that enough proof? I've got three of them nails fit. Can we really say that everywhere on that sphere that the force is radiating outwards? How can we prove it? Do we want to take the time to put tissue paper all over it? Can anybody think of an easier way to do that? Put my hand on it, what, speak up. Let me say five.
Guys.
One thing we have to do. Hello? I have the floor. One thing we have to do is make sure we can get ourselves isolated from ground. What is ground? Limitless sink. I can keep dumping electrons on without getting a charge. So what we're going to do is take this nice piece of styrofoam.
Guys, listen.
Kevin, can you, I just should not get knocked on my fin. What we're trying to prove is that if I have a sphere and I get it charged, the electric field will always be at right angles to the charge. My head is roughly spherical. So I'm going to transfer a charge from that sphere through my body onto my head, which will then get into my hair, and hopefully it will stand on end when you're ready. Now the first thing you'll feel is a tingling in your scalp. And then we should see and we then can see that the electric charge is collecting all over my body. And if I step off, I'll get a shock. And if you don't believe it, and I'll get charged, I want you to prove something.
I'll do it.
No, I want to ground you.